Okay, so in this unit, we're going to talk about randomness extractors. Quite briefly, I mean, you can give an entire course about randomness extractors, or really or any part that we talked about, like expanders and pseudorandom generators and space-bound normalization and so forth. But I still want to give kind of the gist of what randomness extractors are, and also present Zev Dvir's beautiful construction of merger based on KKs. So it's a paper by Zev and Avi Vigderson. So what's a randomness extractor? So informally, it's an algorithm that kind of extract randomness, and hence the name, from imperfect sources of randomness. Namely, it takes a sample from a distribution and somehow produces a more beautiful sample, something which ideally would be uniform or in a sense close to uniform. So here is a definition, like a wishful definition, and also an accurate of a randomness extractor. So, it's definitely going to be a function. Think of it as an efficiently computable function, a function. It's going to get a sample. And let's assume we are representing everything using bits. So it's going to get a sample, an n-bit string, and it's going to output some, m-bit string. And the hope is, and we will need to formalize that, is that for every random variable with enough randomness, whatever that means, let's call it x. So x is supported on n-bit string. It's a random variable or distribution. I kind of don't distinguish the two here. You want that this thing is in some way that will formalize close to uniform over m bits. Okay? That's the goal. So if you have enough randomness here, and in a sense it should be at least like m bits of randomness, then the output should be maybe not exactly, but sufficiently close to uniform. Okay, so now we need to formalize two things. First is what does it mean enough randomness? And the second is what's this thing, right? So the way we are going to, I mean, you can think maybe we are going to use kind of Shannon's entropy function, which is usually, written something like that. Yeah. But a different way of thinking about it, maybe a better way is so you're sampling x from x, and you're asking what's the probability for it to equal little x. But right, so this is the expectation. But the point is that Shannon's entropy function was meant to work on average. So you're getting a lot of samples, and you ask, typically what's the number of bits I need to represent a sample, and so forth. The extractor that we are talking about here is going to get like one sample from the source. So it doesn't have the luxury of waiting along typical inputs. It's kind of a worst case thing. So what we are going to essentially do is replace that by a mean. Okay. So let me define that. So the mean entropy, that's the name for it. The mean entropy of a distribution or a random variable x is exactly what we kind of said. It's denoted like that with an infinity in a subscript here, and it's the minimum over all x in the support of x, you'll see, of log 1 over probability capital X equal little x. This is little x. Okay. So that's the definition. It's kind of the mean version of the Shannon's entropy. And you can ask, why is this kind of log scale and why mean and so forth. So, just to kind of motivate it a little bit, what's the mean entropy of a constant variable? It should be zero, right? If this measures randomness, a constant variable has no randomness, it should be zero, and it is, right? Because in a constant thing, the minimum is just, there is one element in the mean, and this is 1 for that element, so the log of 1 over 1 is 0, so that's great. What about the entropy of the uniform distribution over n bits? Right? If we did things correctly, it should be n. And it did, right? In this case, all of these expressions are 2 to the minus n, so you get your n back. And like in general, if your distribution is like uniform over k bits and the rest are fixed, then this will be 2 to the minus k, so you get k bits of entropy. And more generally, if you are uniform over 2 to the k strings, so it requires, you need k bits to generate and sample, it's also going to be k. So it kind of makes sense. The mean entropy, I mean, I'm giving it like that, but it's in some sense you can show that up to some small detail, this is the weakest assumption you can have on the source, so that you'll be able to extract randomness from it when properly defined. So that's not just a definition, in a sense it's kind of the definition. So that's what we mean by enough randomness. So after we'll deal with the output, we'll plug this back in and I have the right definition sitting here. But that's what I want to say about the mean entropy. I'm going to assume that X has some mean entropy. What about this exactness or closeness to uniform? So we are going to define another important notion of statistical distance. Maybe you've seen it already. So if you have two variables or really distributions, so the statistical distance between two variables x and y is denoted by SDXY, and it's called statistical distance because you're going to perform statistical tests, and in order to distinguish x from y, and based on your success, that's going to be the distance. So what can you do? You're given two distributions, x and y, or two samples, like two random variables, say on the same support. Otherwise, you can take the union of the supports. And your goal is to distinguish them. And so the thing you will do is you're going to find the test, maybe there are many, but a test that will distinguish them, the two the most, right? So if you write it down, it will be like a max, everything is finite, over all possible tests. So these are, subset of the support. So this is the support, the joint support of x and y. And that test you're going to test against x and against y. Right, so what's written here is that you're going to figure out all possible tests. I mean, that's not efficient. All possible tests, and you're going to check what's the probability that x is, if fails or succeed in the tests are in y, and the test that will help you distinguish them the most, that determines the statistical distance. In pictures, it's actually more intuitive. So in pictures, say this is D, the support. Like for every point here, you have a point in D, and this is the reals. So this is 1, this is 0. And just consider the two histograms of x and of y. So maybe this is the histogram of x, right? Meaning this is the probability that this element will be sampled from X. And maybe this is the density, the histogram of Y. And, tests are subsets of T, of the X-axis. So the best test here, or our best test here, is the following. So it's this one. Right, this test always favors Y to X, so it maximizes this sum in absolute value. Also, the complementary test does that, right? This one. They get the same value because the sum of both areas under the curves is 1. It's the same. So the point is that this test is a maximizer for that, and this area here is the statistical distance, right? Good. So from looking at that, you can see that the statistical distance, you can also compute it by taking the L1 norm, like point-wise rather than test-wise. L1 norm between these two curves, and well, divided by 2 because there are 2 contributions. So the statistical distance can also be written like that, where I think of these as vectors. So x of little x, at index little x is the probability of x2 equals x. And from here, you can also see that this is actually a distance. We call it a statistical distance, but it's true to his name. Okay, so that's the statistical distance. And now we are finally ready to say what's the definition of an extractor. So a K epsilon extractor, K is going to relate to the mean entropy of the source, and epsilon is the error that you want to guarantee, is a function x from 0, 1 to the n. Oh, that's ugly. From 0, 1 to the n to 0, 1 to the m with the following property, such that for every k source x, and by k source I mean a source that has entropy at least k, mean entropy at least k. That's what I mean. That's part of the definition, really. What happens is that the output of the extractor is epsilon close in statistical distance to uniform. In statistical distance, namely the statistical distance between this random variable and uniform on n bits is most epsilon. Right, so that's the definition of a K-epsilon extractor. Unfortunately, that doesn't really exist. So you can kind of immediately see that, and even in really modest parameters. So even if m is 1, right, and less bit you want to output, the easiest the work is. And even if k is n minus 1, which is a lot of entropy, you're 1 bit shy from uniform in a sense. Well, okay, every extractor is like a 1 extractor in terms of error. So, and assuming epsilon is most like 1/10 for 1/4 or something, you can't have that. You can't have an extractor that outputs 1 bit from n minus 1 bits of entropy, which is a lot. I mean, you wish a little and get a lot, even with like constant error. And the reason is that because given the extractor, you can always cook up this following source. I mean, one of these two sets will be the pre-images will be larger than 1/2. So let's for simplicity, let's assume it's this one without loss of generality. So consider the random variable which is uniform over that. Okay. This random variable has entropy at least n minus 1 because this is of size at least half times 2 to the n, so 2 to the n minus 1. So this entropy is at least n minus 1. And nonetheless, the extractor is constant by definition on the source. In particular, it's not close to uniform. Okay. So that led, because of applications and so forth, that led researchers to consider two types of extractors that actually exist. So there are three types, or you can divide it maybe a bit differently, but three types of extractors. First are the seeded extractors. So what are these? So seed extractors are, extractors as we had before. But now they also get a seed. And by a seed, I mean you get some extra bit of randomness, few bits of randomness that are uniform and are independent of the sample that you're getting. And using these bits, you want to extract the randomness. So usually you think of D as much smaller than N, hopefully like log N. And it's not your intention to output these bits. It's your intention to use these bits in order to kind of access those. Okay. So yeah, I'll talk about this in a second, but let's keep them as is. So it's called seed extractors for good reason. And these were introduced, explicitly by a paper by Nissan and Zuckerman in order to get some result on BPL. And already at the get-going, when they defined them, they kind of got fairly good constructions. And today we have nearly optimal construction, depending how greedy you are of seed extractor. So this is a really kind of a success story in pseudo-randomness. We understand these constructions very well. They have many applications, some beautiful things going on inside them. We'll see one today, and so forth. The second type are the two-source or multi-source extractors. So here you're not going to assume you have a seed. You're going to just say, okay, I'm just going to get not one, but two samples. Like, I'm going to get samples from two possibly different but independent sources. Okay? And the hope is that, you can play once against each other in a sense. And you consider three source extractors and so forth. Two sources is the hardest. You have less sources to work with. And these things were really hard to construct. So there is a very simple construction that we will see next time, the inner product construction. And it was essentially the only construction for like 20-something years. And then two other construction came in, one by Ran Raz and one by Rugen. But following actually a sequence of work on a variant of seeded extractors called non-malleable extractors, which we will not talk here, a lot of progress was made on two-source extractors. In fact, by this point, we have essentially optimal construction of this. Okay. And the breakthrough work here was by Ishan Chattopadhyay and David Zuckerman. And also interesting to note is that this problem is related, in fact, harder than the problem of constructing Ramsey graphs. So that's, constructing two-source extractor was known to be a difficult problem. And, now we know how to solve both problems, Ramsey and these. And the third type, which is not really a type, is like a meta type, are structured sources. So here you're going to say, I have no seed, I have no two sources. It's just that my source is going to have some more structure, than just being like K source. For example, it could be maybe an affine subspace, which may look weird at the beginning, but it's a very natural question. Or maybe it's efficiently sampleable. I mean, maybe the source of randomness, the randomness is produced by something which is efficient, either space-wise or time-wise, and so forth. And, there are many works on these. They are really interesting. And interestingly, a lot of everything, both here and here, uses seed extractors in particular. Also, I mean, two-source extractor technically also fall under this category because a two-source extractor, you can think of it as getting an extractor as like a one source, but the source is structured, maybe it has two parts and they're independent, and each is a k-source. But that's, we shouldn't go too formal here. It's really kind of a different story. Two-source extractors are two-source extractor, and by structure, we usually mean something more structured than just, where the partition between the sources is. Good. So, I don't want to spend, I mean, I do want to, but I don't have much time to spend on each of these. Instead, I'm just going to tell you that the construction of seeded extractors, all constructions that we have, we have some constructions that are very good in some regime of parameters. So, for example, if you have a lot of entropy, if k is very close to n, then you can work out by yourself that a random walk on an expander is a kind of a great seed extractor. But usually the problem is, to handle the case where the entropy is low. And it's almost never really the problem of outputting many bits or making sure the error is good. I mean, when you construct extractor, you can think of constant error and m equals 1 if you want. The real issue is with a short seed to try and access like low entropy sources. Okay, that's kind of turned out to be the problem, at least with the techniques that we are having and working with. So instead of constructing a seed extractor, because we won't be able to do that in this course, unfortunately, because of the weeks we lost due to the war. So I'm going to give you one ingredient that's used in some of the constructions, and that's called a merger, a randomness merger. And I'm going to consider the simplest case of that also. Okay. The other ingredient, which actually is even more useful in constructions, is that of condensers. But again, I'm just not going to have time to talk about all of this. So I'm just going to talk about mergers today.